Thank you very much. Okay, so I was given an impossible task, so I should not be nervous at all because I will fail regardless of what I do. So that being said, I can't resist to share an anecdote. So Sasha Polyakov used to teach every year at Princeton class. The title really didn't matter. It was Random Thoughts on Theoretical Physics. And he liked to say that the best way to give a great lecture is to not prepare at all. But then the success rate is 50%. So that's so let's see how that goes.
So one of the two talks will be good.
Yeah, exactly. So
look, your point is not to lecture, it's to deliver the joy.
Yes. There you go. So maybe that I can achieve. So a disclaimer: there are no references. So you can be upset, but there are no references. So even if you worked on it, on the field, I will not reference myself, but for now. So just if you really become interested and excited about this topic, then there are these three references to white papers that I participated for SNOMAS, one on the phenomenology and future observations to probe inflation. This was done with the editorial help of Ben Valish and Kimi Wu, who's local here in California, plus 19 co-authors, and also a white paper on the cosmological bootstrap. Now I have a little challenge with, I just wrote the initials, Bauman, Green, Joyce, Peyer, Slate, Tarona. Okay. And also in December, if you want to have a snooze time before going to bed, you can play on YouTube. I gave 9 hours of lectures on this GGI, on the string theory school. So it's a long version. It's the director's cut of these lectures. Okay? So one should start the talk, in my opinion, with the end, so that then you either phase out or you become excited for the rest. So I will tell you the main messages. So the idea that has surfaced or become clear in the past decade or so is that you should think of the early universe as some sort of particle detector that operates at an unknown but potentially extremely high energy, perhaps the most energetic experiment that nature performed for us. We don't really know what this energy is. I'll reveal that. But one should think of the qualitative analogy, and quantitatively you can push very far this connection to collider physics. And cosmological correlators are really the scattering amplitudes of these experiments. Okay? So a lot of technology for scattering amplitudes, for perturbative QFT, that is being showcased in this conference can be exported to the cosmological context. And we're still in the early days of this exploration. We know very little about the structure of cosmological correlators compared to what one can do in flat space. So computing these correlators as a matter of practice, it's complicated, even at tree level. In the afternoon, I'll tell you about things that we try to do at tree level. At tree level is already complicated. It's a beautiful endeavor. It connects to the physics of scattering amplitudes, and we use some inspiration from also other areas of physics, like holography, from conformal field theory. And it's ultimately about understanding quantum field theory in curved space-time, and also the theory of the birth of the universe, so we better understand it well. Okay, so so if you're excited, here we go. If you're not, I have nothing else to offer you today, unfortunately, just theory of the birth of the universe, not much else beyond that. So for the morning session, I'll focus on phenomenology. Okay, so there will be a low density of formulas, lots of words, lots of pictures, some qualitative view of how to think about this subject. So I start with the figure that I always draw when I give these talks, but so I'll start with the phenomenology of cosmological correlators, and it's useful to draw a timeline of the universe. So time goes up, and let's see how the color situation is here. 1, 2, 3, 4. Okay, that will do. So here we are. It's us. And And we observe stuff at large scales around us. We observe galaxies. These are my, despite drawing these maybe 100 times, this is still my best shot at a galaxy. So these are my galaxies. And they sit on some scaffolding of dark matter. We can observe indirectly through lensing and so on. So there are raisins on some cosmic pudding, some cosmic web. And then if you keep observing, this is a big tracer. Actually, it's what's going to push our understanding of cosmology probably for the next decade. Will be largely driven by galaxy surveys. But of course, the crown jewel of this field is if you look backwards in time, then you see this snapshot of the early universe when it was very young, 350, 80,000 years old, which is the microwave background radiation. So it's fairly uniform, around 3 Kelvin, with small perturbations. And I just changed my cell phone, but in Pisa there's a shop where you can print whatever cover you want for your phone, and I had a map of the CMB, so I like to show that, but unfortunately my phone now has a boring case, so I can't show that to you. But you saw in yesterday's talk this beautiful map from Planck of the temperature perturbations. So we know that it's fairly uniform, but importantly not exactly uniform. So there are temperature fluctuations of 1 part in 100,000, the difference between a hot and a cold spot, and that's a treasure trove of information for us. So the way so there are little cold spots and hot spots and so on. So it makes this map that Jung showed you yesterday. And that's it. So we have CMB here. We have large-scale structure. We have a whole dark age of the universe that we can't probe directly right now, that we have the dream of one day probing, maybe with 21 centimeter line spectroscopy. So neutral hydrogen would absorb CMB photons and emits this 21 centimeters radiation. This is, of course, the holy grail of observational cosmology. Just to give you a ballpark, if you do some mode counting, pixel counting, there's roughly 1 million CMBs worth of data here. So I'll just bring that up later in the talk, just to say that despite the fact that we squeezed a lot of juice out of the CMB, there's still something left over, and now we're going to squeeze quite a bit of it from galaxy surveys. Humans still have the potential to do much, much better at understanding the early universe. This is a hard measurement. We have a monopole that is from our galaxies, and anyway, so we haven't achieved a detection of this radiation from the dark ages yet, or even from relatively low redshift. Very good. So, so how do we characterize the distribution of galaxies in the microwave background? It's through correlation functions. So the typical plot will look something like this. Here you put things in redshift bins. You can think of it as a tomogram, or it's easier to think in terms of wave number. So you go to three-dimensional space. There's translation symmetry. You talk about wave numbers because of rotational symmetry really only depends on the absolute value of the wave number. And you compute here the 2-point function of the density contrast compared to the average as a function of k. Okay? So this is essentially saying if I see a bunch of galaxies here, what's the probability that I see a bunch of galaxies over there as a function of separation in the sky. Okay? And you can compute this curve, and the curve looks cool. It goes up, it goes down, it has wiggles, and you take a whole cosmology course to understand where the curve comes from. It knows about the matter era of the universe, the radiation era of the universe. There's tiny baryon acoustic oscillations, the important ruler of the cosmic history of the universe. And you can repeat the same exercise for the microwave background. You can compute the statistics of the temperature fluctuations. It looks like this. Now, because it's a 2D map, you go to the celestial sphere, and it's a function of multiples in the sky, and it has these peaks, and then some damping tail at small separations. So here you infer the amount of dark matter. You can tell the value of the Hubble constant and so on. And here, if you look at large scales, the universe is rather young, so the perturbations didn't really have time to time evolve. So here you're more or less looking at how the perturbations were at the onset of the universe, at the hot Big Bang. So if you go, our standard model of cosmology, if you go to the naive time equals 0, now I see I did bad management of the figure. Let me put time equals 0 somewhere here. Okay. So this is 0. It's the hot Big Bang. Then you see that to explain these perturbations, we need to have not exactly perfectly homogeneous initial value surface for the universe. So our standard model of cosmology has dark matter, baryons and photons, dark energy, and so on, but it needs special initial conditions, correlations, that are imprinted at the hot Big Bang at long distances. So the way to characterize it is, do you see here in the bottom, in the back, is it okay? Yeah? So this is a function of wave number, because it's in the 3D surface. If you look at this is called the curvature perturbation. Sorry, malfunction. This is called the curvature perturbation. It's essentially the local scale factor of the universe. So the universe will look. I'll define it in a second, okay? But so the zeta variable, you can think of it as the local curvature of a little patch around the given point. And you need that to explain these curves, okay? So you evolve. This is not my analogy, so Ichiro Komatsu, when he gives talks about this, he talks about miso soup. So you have to take miso soup and you put little pieces of tofu and they create little ripples and then it creates some rippling pattern in the miso soup. So this is the location of the tofu blocks.
What's that dark matter in the miso soup?
That's left as an exercise for the reader, for the listener. So to explain the data, you need a very flat, because I multiply by k cubed, you need all k cubed. If you went like 1 over k cubed, this 2-point function, it would be scaling variance. It's a simple exercise in Fourier transforms. But it has a small scale dependence. There's a little bit less power at large k at short distances, a little bit more power at low k at long distances. And these are 2 of the 6 numbers that we need to explain the universe. So the overall height of this curve is parameterized by some cosmological parameter, the amplitude of scalar perturbations, and then we have a small scale dependence.
But how do we will use it if it is kind of a real initial deviation, or it is like fluctuation indeed? I mean, I'm not sure whether there is much of difference, but still, you see whether it's kind of profile of something initial, or it is fluctuation which will come naturally.
In the standard cosmological model, it looks a bit crazy because at 0 time you have correlations at long distances, but we're going to fill in the picture so that this state is generated from some earlier time evolution.
Yeah.
But if you're just looking at the data, trying to explain the data, what's called the CDM model, you just postulate that there is a time 0, there are these correlations, okay? Which is, of course, far-fetched, but we have a way to, that's why my timeline has some part here. We're going to fill it in, and then there's going to be a causal explanation of this.
So in this way, it does not give you mechanism of this.
Exactly, indeed, yeah.
Particularly low k, they look like they violate causality.
Yes, yeah. Yeah, we call these super horizon correlations because they are, in fact, if you look at the CMB map, and you look at the size of the light cone, so you could imagine that the things could have happened within this distance until the moment the CMB photons start free streaming, the universe cools down enough. And if you look at this angular size, you would think, oh, it's a relatively big angular size in the sky, but it's the typical size of a hot spot in the CMB, so very small. So if you don't need to go this angular direction to have a causality problem. If you go just 1 degree, it's already causally disconnected because the universe is rather young. There's not enough time here.
I thought inflation was to get around this causal problem, right?
Well, imagine you're going to the greatest hits concert of an old band. So and we're still in the opening act, and inflation is about to walk the stage. Yes, so correct. So we're going to fill in this picture with inflation. Okay, excellent. So you just killed my punchline. And, so what's the way to explain this curve is to continue filling in this figure with an earlier phase of accelerated expansion, inflation. Okay, so which is kind of amazing because inflation was not really developed to solve this problem, to give a theory of structure formation. It was trying to explain why the universe looks so homogeneous, and people were also interested in magnetic monopoles at the time, and if there are magnetic monopoles in the grand unified theory, where are they now? How do you wash them out there? Anyway, so it was developed to solve other problems, historical accidents, but the reason why we love it so much is that it naturally gives a theory of structure formation of the universe through essentially the Hawking process. Okay, so spontaneous pair production, or Schwinger pair production, or Parker pair production. Anyway, so you can, or Chernikov-Tajirov, as usual. Soviets had done it before everyone else. So, or Mukhanov-Shibisov. Anyway, so you get these correlations just come from spontaneous pair production. So you have the standard vacuum fluctuations that you have in vacuum polarization in flat space. But because of the acceleration of the universe, the pair gets pulled apart and it goes on the mass shell. It deposits a little bit of stress energy. It's correlated, some sort of EPR pair, and it creates these long-range correlations. Okay? And the kinematics of this accelerated universe is such that this almost scaling variance is easy to achieve. So that's the causal, and now we filled in the causal picture of what's going on. Okay. So our goal is to understand what is this. So what is this period? So just to quote some numbers, because the primordial universe is not exactly, it's not like particle physics. It's not that we are flooded with numbers, but we have two that we can try to squeeze as much juice out of, and we have bounds on other numbers. So a way to parameterize this two-point function is as follows. You write AS on this, and then you take some pivot scale, K star, which is not so relevant, to a certain power, and historically we write it in this way. There are many historical accidents here, so I'm not going to go in a history lesson. So this is a small number that we write as number close to 1 minus 1, okay? So these things have been measured first from Kobe, then WMAP, and finally Planck really nailed this number here with high accuracy. But this had been measured before, starting from Kobe. So I just quote. I hope I didn't mess up, because usually it's written in terms of a logarithm, so I think I still know how to take exponentials. But so this is the amplitude of scalar. It's dimensionless, okay? So there are no units. And NS, as I said, number close to 1. Okay, this is from Planck.
But say, if I will ask you, K equals 0, right? In your curve, so it would be AS, or because or it would be this kind of more complicated stuff. I mean, it's about definition, right?
I think you should think of, we only really probe this in a range of scales. We only really measure this curve for some range of k's, like here, and then we just use this power law parametrization. Yeah.
So it's a k order, k star in a sense.
Yeah, maybe with a decade around the k star to the left and to the right. But actually, it's an interesting question whether at small k there's a deviation. There is some preference of the data to not follow exactly this power law at low L's, and people have been trying to squeeze juice out of this for 20 years. But here there's only one universe to measure, so the error bars are limited by our lack of other universes to measure. So that's, if you had other tracers, maybe different tracers that remeasure this low L part of the spectrum, maybe one could say something about it. Because you're looking at large scales, if you look at this picture here, you're just looking earlier into inflation. So people wonder, oh, maybe there's something about the beginning of inflation that really tells us about this period here. But anyway, this is even more speculative. So these are numbers that we know. And then there are natural questions. So what is this? Meaning, where is it fundamentally coming from? So what happened? And what's even the meaning of this inflation? Okay? So that's really all we know from the data. And I'll try, given that it's a particle physics meeting, I'll try to give a modern take. I'm sure if you studied inflation before, you're immediately drawn to like some potentials, right? Some wiggle, some potential, you roll down some potential. So I know that you want to hear this tune, but forget about it. I got a new guitar, so I'm going to tell you a more modern way of thinking about it that is sort of driven by what we really know from the data.
But you should not tell, you should sing.
I am singing. Okay, so...
Sorry, can I ask a basic question? How are these equations normalized? When you say you measure AS, this means that you fix a normalization of...
Yeah, you need to write... right, so there's some average scale factor of the universe that is fixed by lambda CDM, and then this will be the relative deviation from this lambda CDM at different spots. And one way to think about it is that this zeta is of the order, the temperature perturbation. Okay, so that's, and then this is something that you can measure, physical, and then this is the direct connection. Okay, and so you can see it from here, right? So as this is 10 to the minus 9, then what is 10 to the minus, not 10 to the minus 10 among friends? So zeta is of order 10 to the minus 5, which is the average temperature perturbation in the CMB. Okay. So if I write the metric, then you'll see that. Then once you fix a frame, there is but I don't want to write the formula yet. Where it's essentially the local, it's some breathing mode of the scale factor. You write some FRW metric for our universe, this lambda CDM. You can think of this zeta variable, some breathing mode that modulates the scale factor locally, makes the universe a little bit bigger, a little bit smaller, or advances or delays the time evolution of the universe.
T bar is 3 degrees, and delta T is tens of nanokelvin or something like that.
Micro, you mean?
Microkelvin.
Yes,
sorry.
indeed, yes. That's right. Yeah. Okay, very good. So let me try to give a sort of a particle physicsy approach to this question of what is zeta. I'll keep that here so you remember the joy. So you should think of zeta. You should think of zeta as some sort of pion. It's a Goldstone mode from time translational symmetry breaking. So the idea is that if inflation happened, then the energy density of the universe is changing slowly, and there's some natural foliation of the universe that inflation peaks. There's a natural clock. So it slices space-time with some clock that we don't know its origin, but you just assume that the clock exists. And then, so you broke time translation symmetry, and this zeta variable is the Goldstone mode associated to this time translational symmetry. So you can write an effective theory for it. So it's called the EFT of inflation. Okay, so it was developed, it was written down in 2007, more or less. It's a bit like the nonlinear sigma model adapted to this symmetry breaking pattern. So there's if you wish, there's a nonlinear sigma model for zeta.
But this is also a model would be for kind of compare with the main wall. So it would be the C dimension would be on the wall, right? And moving time. So it means that it involves the whole space, the whole space, right?
Yeah, well, one way to think about it is if I draw this picture of inflation here, then the natural clock slicing of constant energy densities, and this zeta parameterizes if I get moved up or down here. So it kind of takes this average energy density surfaces, and it's
still like a moving wall.
Yeah, yeah. But in time.
Yeah, in time.
Correct, yes. So there's this nonlinear sigma model for zeta, and then the question is, well, what UV completes it? Okay? So, and we know that there are different ways of doing that. So, so what UV completes? Oops, completes zeta. And the short answer is we don't know, okay? So this is an important lesson. We don't know. We should not keep wearing the hat of history of how this theory was, how we got to the theory, because there is a strong bias that comes from the first models that we wrote that explain this. But we really don't know. So we should be open-minded. So what's the simplest way of UV completing the nonlinear sigma model is with a linear sigma model. Well, this is in the standard model is related to the Higgs. Then you can, once you have the Higgs sector, you can add additional particles on top of it, electroweak theory, and so on. And this is what people call slow row inflation. Slow. Let me write it explicitly. Slow row, which is historically the first thing, and still where 95% of the activity is concentrated. And a lot of our observations and biases of how things should happen assumes that this is the UV completion, but it's an assumption. We don't really know. Okay? And given that I think this audience will resonate, we know that there is another way, right? That it can have strong coupling dynamics, something like QCD. Is zeta a composite, for example? And I don't really have a benchmark example of how this would work in the case of inflation. I think this is an avenue that hasn't been explored, probably by a factor of 10 to the 5 between this approach and this approach. But they are, I think, equally.
Why do you need any non-abelian structure? I mean, it just could be a single scalar field, right?
It can be, but it doesn't need to be. I'm just saying that we don't know anything. These are the only things we know, okay?
But there's no indication of a non-abelian structure,
right? We don't know. So we should map everything that is possible and then let experiment and observation decide. Because the searches, sorry, I'll let you chime in a second. The searches are driven by what you tell the observational people that you should look for this. there is no like blind agnostic search for every, so you need to know what to look for. So yeah,
No, I just was trying to say that we do not know even whether it's abelian.
Yeah, right, we don't know.
So in this way it's open.
Yeah.
All you need is some flat direction, but not a...
So
No, there's
that's
no
single
there's no non-abelian
That's right.
structure.
Because there may be a third arrow for
But
multi-field.
the theory behind it.
Yeah, I meant here Higgs electroweak. I mean like if you wish weakly coupled UV completions, you could imagine that there are many scalar fields, and you pick
So
one
you would
direct.
still put that
Yeah,
in
yeah,
this left
yeah.
arrow.
But
Yeah.
if I can ask another question that builds on this analogy, so the same thing is actually true of electric symmetry breaking in some sense. We assume that electric symmetry breaking is linearly realized, but technically the data is consistent with nonlinear, with something different, with non-decoupling physics.
Right.
However, so you would say these two branches also are equally possible, consistent with data. However, the fact that many things that we could have been non-zero are zero mean that in reality, the space of non-decoupling scenarios that is still consistent with data is actually fairly tightly constrained.
I see.
Is that true here, where there's the things that could have been non-zero but are zero give a preference to slow roll, or really you would say it's
To be honest, I don't think we understand what are the predictions that this type of scenario would make. So I can tell you a little bit, maybe towards the end of this first session, I can tell you a little bit of how I'm trying to approach this question. Not trying to build a full-blown model, but just asking if there is a strongly coupled sector, how would you see that in the data? But I don't know.
But original gravity which you have, okay, if it would be some places where there's a large density, whatever, it could be just gravity itself, right? Or it's impossible.
I mean, there's something that people call gravity on its own. It's called Starobinsky inflation, which is really slow roll inflation. Just you do some filter definition, looks like pure gravity, but it's really gr plus a scalar field. You write r plus r squared, you say, oh, it's gravity, and you attach some words to it, but you do a filter definition, and it's a scalar field in a flat potential. So it's slow roll inflation. So yeah, I mean, it is interesting to characterize different types of slow roll inflation, but I would put all of them under this umbrella. Okay.
So you would do it with pions in the case of QCD or what?
Well, then I think that the idea would be that you need. So what I didn't say is that there is a typical energy scale during inflation, and this particle is very light compared to this scale. So what you need to achieve is some QCD-like model where you have a scalar at the very bottom of the spectrum and at least a little bit of a gap. And if that's easy to do, then I would identify the lowest lying mode as this curvature perturbation.
This is usually called a dilettante-like scenario, not a Goldstone scenario.
Why?
Near conformal.
It's break, well, at least
No,
break
no.
has space-time symmetry instead of an internal symmetry.
Yeah, right, exactly.
But
Usually you think of this as more like a dilettante experiment.
yeah, but this, I don't think that this is a dilaton. This is really the Goldstone for this time translation symmetry breaking, because the dilaton is when you break conformal symmetry by introducing some scale, some mass scale. Well, here we're introducing a foliation, so it's time translation that's being broken. But
It's not an internal symmetry, it's a
yeah, sure. But
It's a very different thing, right?
yeah, it is different, but it's the same also in the sense that it's a Goldstone mode.
It's not the same.
Anyway, so it's from the time translation symmetry. So it's okay. So how do you test the microphysics of inflation? How do we? And that's where these things come into play. So the question is, how do we test what the micro physics of inflation is? And there are many, well, essentially it boils down to other correlation functions beyond zeta zeta. So correlations. And I'll highlight what can be achieved in the immediate future boils down to these three things, which is in that inflation white paper we focus on. First of all, two-point function of other fields. And of course, the most spectacular example would be the graviton. So it's a gravitational theory, so space-time itself is fluctuating. So you could have tidal forces here and here, and you would induce a graviton two-point function. This, as I'll show you, mostly biased by this simple analysis of the basic models of inflation. We're willing to bet that we might be around the corner from a detection. And if it's true, then it implies that this energy scale, the typical energy scale during inflation is huge. Okay, it's not really completely model independent, but it's pretty robust statements. If we detect this in the next decade, then probably the Hubble scale, the energy scale during inflation, is something like 10 to the 13, 12 GeV. Okay.
But why they would not be related? Say you have variation of zeta, right?
Yeah.
This variation of zeta leads to variation of gravity as well, right?
Yeah, but the zeta is controlled by in principle, it's controlled by a different scale. There's a scale in which So I'll draw a picture of all the scales, and then you see. But here, because it's really gravity, is controlled by the ratio of the typical scale of inflation in Planck units. And that's where, here you say you know that there is some separation between two scales, but you don't know what they are. I mean, people look for other fields beyond the graviton. They're called isocurvature modes. Like Lance was asking, you could imagine that there is some maybe a linear sigma model or sigma model with an interesting curvature. And then you would have the direction in which the universe is inflating, but maybe orthogonal directions. There could be perturbations around those. People also look for these. So these are, let me call them phi. They're called isocurvature perturbations. So I'll probably not say anything about these. They're interesting, but I just have finite time, so I'll focus on saying something about this later. Then something I'll not mention, but it's in the white paper and people are very much interested in, is in primordial features in zeta zeta, meaning you take this function here and you add some wiggles, for example. You can imagine that it's 1 plus sine of k, and you try to put a bound on the coefficient that multiplies the sine. And there's some natural models in which this could happen. You could imagine that there is an additional field that modulates the average energy density here. And one thing that will become clear as we discuss things more and more is that if you look at different pairs, they are really sensitive to the average energy density at different times. So if I look at a pair here, it really cares about pair production around this energy density compared to a pair that is produced here. Maybe it cares about this energy density. So if there was some modulation from some additional field active during inflation, then you would see also a modulation in the two-point function of the scalar perturbation. So people also look for this. And we have bounds. We haven't seen anything. We have bounds.
Can you consider kind of more than double correlator for, say, 3 or zeta or 4 zeta?
So, you can also consider higher point correlation functions.
Sorry.
It's good. Keeping me on my toes. So, higher point correlators. And, okay, I will probably for this morning session, I'll focus on this. Maybe I can't resist. There's a little comment about this that is kind of neat. If I forget, you remind me what about the comment on gamma zeta zeta later. And when we go to mathematical physics to actually trying to compute this and writing formulas, I'll go to 4 points because it's easier think about that example. Okay.
Wouldn't primordial features be reflected in the higher point correlation?
They would be, but every time you add a zeta, you pay a 10 to the minus 5 price, and so you would have like some almost scaling variant piece plus a modulation on top of it. So you would first need to see this and maybe look for modulation. So here it's easier. So
the analog of that in collider physics too is called multi-Higgs production.
Okay. Very good. The other reason why people care about this is because we measured zeta and we haven't measured gamma, so if the amplitude of gamma is too small, maybe you don't want to pay the price of two of them, you only pay the price of one of them. So anyway, so that's another reason why there is interest in this. But there's also another cool thing that is related to representation theory of the de Sitter group. But I'll just let you that simmer in your mind for a while. And,
zeta is forbidden by symmetry?
Say again?
A two-point function between gamma and zeta is
by rotational symmetry. Yeah.
Okay.
Yeah. You could imagine, for example, zeta and some other field phi, and if you measure this cross correlation, then it would be a clear indication that you really broke the almost de Sitter symmetry of this space-time. Okay. So let me, this is a figure, is in this no mass paper, but I think it's useful. So these are the energy scales and the observables. Okay, so let me draw the usual energy ladder here, and here's the top is M Planck. Then there is some UV scale that we don't know of, where this whole inflationary Lagrangian, wherever it comes from, probably breaks down, gets strongly coupled. Then there's some typical, then there are other scales here in between, and there's a scale F, which is, if you wish, the Goldstone decay constant, which is the scale beyond which these scalar perturbations really get strongly coupled. And for example, in slow row inflation, what I didn't say is that the UV completion here is you write down a potential phi, V of phi. And then the idea is that the effective, the potential energy acts as a cosmological constant that drives this inflation, and then you have small perturbations on top of this classical history, and these small perturbations are related to zeta. But of course, if the perturbations become as big as the typical rate in which the scalar field is rolling down the hill, the theory strongly coupled, doesn't make sense to break it into vacuum expectation value and perturbations. This for slow roll inflation, so this scale is set by the kinetic energy of the scalar. But if you are completely agnostic, there is a scale F associated to the scalar sector. Then very importantly, there is the Hubble scale during inflation, which is approximately constant. And then there's some low energy scales here. There's zero here. There's some low energy scales that we don't really know about. Let's see if I do it like this. Okay, so there are things we have measured and things that we hope to measure. So let me show how they play with these scales. And it will become clear that the situation is still rather uncertain. So things we measured are AS and NS. So AS is really connected to the ratio of these two scales. So the amplitude of scalar perturbations is controlled by the ratio of the Hubble scale during inflation and the scale in which the perturbations become strongly coupled. Then NS, as I'll show you, is connected to some low energy scales that is model dependent. So you need to get a small number out of it, and you'll see that it's a small number in Hubble units. So I'll do the case of slow roll inflation, and then we'll see what these scales are connected to. And unfortunately, there's not a single scale, because otherwise we could make a prediction. But we're not able to do that. So this is measured. And what the target is, so this is what cosmological surveys would like to detect, constrain, are related to, so primordial features, for example, they would know about maybe something about these intermediate scales here. So you can probe this whole spectrum. I didn't define what a linear is, but just so when you stare at the figure, it's no mass. This is just some linear feature in the power spectrum when you take k cubed zeta zeta and you write k over k star to ns minus 1, you add 1 plus a linear times, now maybe k, oh, I don't like this, maybe, yes, sine of omega k plus delta. It's called a linear. You might be, why linear if it's sine, but it's linear in the argument, because as we'll see later in the talk, you can have features that are oscillatory but logarithmic in scale. So just to tell apart, it's linear in the argument of the modulation. So a linear is sensitive to this. Then there is something that is related to higher point functions that has a set name, FNL, also some historical accidents that in principle could probe all the way to the UV completion. So higher point correlators would tell us about the UV completion of the scale sector, so we should be able to go climb up all the way here by learning about this FNL. And finally, there are gravitational perturbations that, as I said, they are sensitive to another ratio of scales, not H to F, but H to M Planck. And of course, this would be great, because you would really nail what H is. Okay, so this is...
Just to be clear, an arrow means you nailed the ratio of two different scales.
That's right, yeah. But here I already know some ratios, and so for example, if I measured AT, because we know what this is, then we would find out what H is. And consequently, we would also know what F is.
So NS is supposed to be close to 1, so it's not just a ratio of scales. It's something else.
Sorry. Yes, it's a small number. Yes. Yeah, it's really bad notation, but it's the problem of history. So you should really think of a small number. By accident, we write it as order 1 number, minus 1.
Makes the measurement look more precise.
I guess.
Like measuring
Good.
G instead of T minus 2.
Yeah, exactly.
Good for PR. Okay, so just a few ballparks. So a linear is constrained to be less than order 10 to the minus 2. I just deleted what a linear is. Of course, for a range of omegas that you can put these wiggles on top of the power spectrum that we have measured. But ballpark 10 to the minus 2. Then for the 3-point function, I need to define, I will go in gory detail about what it is later, but just as you take the 3-point function multiplied by k to the 6, that's what scale invariance would tell you, and it's of order this FNL, times some shape function. Now you measure a function because there's 3 points, it depends on the triangle. There's some shape function, that's a very interesting business of what the shape function encodes about the physics of what's going on. And again, by historical accident, you normalize in the wrong units. You normalize in units of the 2-point function squared, because everything is dimensionless. You're allowed to do that, but it's really because I'm on the record, it's really not a great way. I would probably use different words. Otherwise, it's not a great way of parameterizing, because I'll quote the number and you say, wow, this cosmologists really suck at constraining this. But you see, you're paying a price of 10 to the minus 5. So FNL is less than order 50. So it's pretty damn Gaussian. It just looks like a huge number because you're measuring the wrong units. Okay, so, and then finally, k cubed gamma gamma as AT. There is a world.
But that number 50 it depends on the shape too. So
Yeah, that's why I put Twiddle. I didn't explain what S is.
We'll do that later.
It will, let's say, it will run from 50 for some shape down to order 5 for the shapes which you can constrain the best. Yeah, there was a world, if you're been around long enough to know about BICEP, that we were thinking about measuring this, but this now looks completely out of reach. But at AT over AS, we call the tensor to scalar ratio, and we know that it's less than order 10 to the minus 2. Okay? So we know that the gravitational perturbations are at least an order of magnitude weaker than the scalar
It
perturbations.
really is defined as NT and not NT minus 1.
People knew better by the time they understood. Yeah. Indeed, yeah. Okay.
These numbers are all Planck?
Yeah. Maybe a linear, I'm not sure that I took this from another paper, Ben Valish and Dan Green and Anges Lozar. I forget all the authors, but they were doing targeted search for this A linear. I don't remember if it's quoted on Planck, but I imagine that they searched for this primordial feature also. This is mostly driven by BICEP, actually, and Planck, joint with Planck. This is still dominated by CMB experiments, and now large-scale structure experiments are competitive with WMAP, more or less an order of magnitude weaker bound than these.
So maybe at this point I can sort of restate my question. Like again, it seems like a simple model of slow inflation, sort of linear sigma model. You know, the first two of these might be 0, and then AT over AS probably depends on how old our inflation.
Yes.
Whereas just a general arbitrary nonlinear sigma model, you expect these could take arbitrary values, and so the fact that so far you've seen 0 does tell you maybe a little bit that it's consistent with the linear sigma model. Is that fair?
It does, but then I would say that you're so far from the prediction of the linear sigma model that there's still a lot of room for it to be some more sophisticated UV completion. So I will review this later, but the linear sigma model, even if you push things to beyond any reason, you will not be able to get this, you get this order 1. So you'll never be able to achieve FNL bigger than 1. But if you see FNL, I don't know, order 10, then...
But like an arbitrary nonlinear sigma model, FNL could have been at 5,000 or something, right? So somehow the fact that there was a range that currently has been excluded that tells us we're in the space of total UV completions, we're getting closer and closer to a linear sigma model.
Yeah, if you think about it that way, then I would say that you're kind of halfway in between the fully strongly coupled thing and the prediction of a very weakly coupled model. So the prediction of a very weakly coupled model would be FNL even like much lower than 1, order 10 to the minus 2. So fully strongly coupled would be maybe 2 or 3 orders of magnitude above this. So depending on how you... I agree with you that both from a historical perspective and from a simple model building perspective, one could bet on slow roll, but it could be around the corner, and if it is around the corner, it cannot be slow roll.
But if you consider 50 to be a large number, that is some effect, right, there of enhancement in a sense.
Yeah, I need to explain how you enhance this, but yeah, I will tell that later. If you embed this zeta into this linear sigma model, like Nathaniel is asking, then the same scale controls two things: is the scale that drives the background evolution and the scale that controls the size of the perturbations. And in order to do both jobs at the same time, you will be pushed into having this FNL always be rather small, at most order 1. So you're still like more than an order of magnitude away from seeing that type of UV completion. I'm just saying that if one is more open-minded, then if it's around the corner, if we see something in the near future, one should consider this type of possibility.
So the observational pessimists prefer the linear model.
Of course, yeah, you can be a pessimist and then we go home, we stop doing primordial cosmology, but I am an optimist. So,
optimists have to hope for
I'm phrasing this question in a pessimistic sounding way. In the analogous question for electric symmetry breaking, I'm also an optimist, and so I share the optimism here. But it is interesting that actually very similar tension in terms of these perspectives is playing out in both kinds.
yes. No, but to be completely fair with David's point, if you think that it's historically what people wrote in the 80s, that is the theory of the universe, then probably this is not achievable in the near future. But if you remember my picture at the beginning, if you get this full tomogram of the universe, human beings in principle can climb all the way down to FNL order 10 to the minus 2 where you would see this. Even it's just not going to be maybe our children, you know, but not us probably.
Sorry,
That seems like
what's the gravitational floor in units of FNL?
NS minus 1, 10 to the minus 2. So 3 orders of magnitude away. Yeah, so there's a point that you have to see something, otherwise just not inflation. So say the gravitational floor. This would be of order 10 to the minus 2. This is fixed by the fact that we measured NS minus 1. So it's controlled by NS minus 1. And I mean, if you measure this, if I just tell you, it sounds so spectacular, but this is the effect. You would essentially measure the distortion on free propagation of 3 scalar perturbations due to their Newtonian potential with each other. So you'd measure the gravitational deviation from the Newtonian potential of the 3 perturbations during inflation. It sounds crazy, but that's the effect. And we're 3 orders of magnitude away from detecting it. So you need more or less 1 million more pixels worth of data. And the 21 centimeters, if you do some naive mode counting, in principle, there's enough juice to squeeze this out of it. But this is very, very much beyond what we can do with CMB and large-scale structure. Here, then, it depends if you're an optimist. If you're an optimist, then you probably, for example, there's an experiment flying, if I remember correctly, this year called SphereX, which is spearheaded at JPL, like not far from here, that is hunting for this signal, this type of 3-point function that we have stronger bounds. It couples very long distance perturbation with short distance perturbation, so it affects galaxy clustering in a rather specific way. And here, how much better we're going to do depends on who you ask. Okay, so if you're an optimist, then or maybe an order of magnitude. If you're a pessimist, order 2. So we'll see.
I should also say, as a program advertisement, if you're here in early March, you can watch the SphereX launch because it's launching from Vandenberg on March 2nd.
Sunday.
Yes, this Sunday. So
At 10:09 p.m.
if you're into rockets or into SphereX.
All you
Or you care about the birth of the universe, then you should go and cheer for it, then you'll go and measure something.
Go outside and look up at the right time.
Yeah.
You'll be able to see it.
Okay, so I have half an hour, is that right? Okay. So I'm doing extremely bad with my time management, but
Great, because you let us ask a lot of questions.
okay. So I will now review. As I said, if you've seen this before, you're going to the greatest hits of your favorite band. So if you haven't seen this before, I hope you will be entertaining. So I'll do a quick review of single field slow roll inflation. Just to set some benchmarks for these scales, and I'll explain why this is the expectation that we could be right around the corner is sort of realized in this simple model. So one could dream that we can measure gravitational waves in the near future. So let me explain how this works. So it's a very simple model. It's just gravity plus a scalar field. So the action is just Planck squared r over 2. And the scalar field we're in curved space, so you need this guy here. So and there's a whole industry of where this potential comes from, why you start at the top of the hill, and you can probably run a whole program trying to explain where this potential comes from and why the heck you start at the top of the hill. The computation for the perturbations that we know and love, which is an adaptation of a method developed by Jim Hartle, who's a professor here, and Hawking, which is a beautiful method that I will review in the afternoon, will predict, it's a vacuum wave function, will predict that you never inflate, that you're here at the bottom. And we're just going to close our eyes and pretend that this is not a problem and assume that we, for some reason, we start here at the top of the hill because we need to inflate, and then off we go. So I'm going to describe the background, the equation of motion, and very quickly sketch what the perturbations around this solution predict. It's an exercise in canonical quantization, but because it's not in flat space, there will be some small novelty. So, by the way, this is standard terminology in the business, but if you, it's really useful to think of phi as a clock. Okay? So let me try to explain that. It's a qualitative point, but it's so important the way people think about this that I think it should be good bar conversation when you go back home. So you see, this scalar field foliates so you have some vacuum expectation value, some classical history, and it's natural to foliate space-time with slices of constant phi bar. So you have phi 1, phi 2. So it naturally gives a clock. And this scalar perturbation is really a local time advance or time delay of the clock. So if I have a little scalar perturbation, then if I had like some constant energy density here, this point gets shifted a little bit forwards in time, and this point might get shifted a little bit backwards in time. So that when these perturbations keep undergoing time evolution, I end up generating, at late times, I end up generating, instead of a uniform surface, which inflation would just stretch the universe and flatten all curvature, you would end up generating some small curvature perturbations. Just from the facts that these small jitters in the classical history either advance you, make you reach the end of inflation quicker, or make inflation last longer. So that ends up creating a slightly bumpy surface instead of a uniform energy density. Okay, so it's really useful to think of the scalar field as a clock. And so how does it... So how does it work? So you take the field phi and you write it as some background thing, plus some perturbation. Now the perturbation is going to depend on time and space. And then through some Higgs-like mechanism, it gets eaten by the metric. So zeta is scalar mode of the metric. So it's a gravitational Higgs mechanism, essentially. If that is already ringing all sorts of alarm bells in your brain, it's because I broke Lorentz symmetry, so all the usual no-go things about Higgs in gravity and so on don't apply. It has 3 degrees of freedom, the metric. It's going to have a scalar degree of freedom plus the 2 tensor, the standard tensor degrees of freedom.
Is the Higgs particle for which field? I mean,
we don't know. Yeah, that's the...
So it's not Higgs of some vector field or...
Here it's of this scalar field phi that people call the infaton, but we have no idea what it is. I mean, people even investigated if it could be the Higgs itself that acquires this vacuum expectation value, and then this delta phi is zeta.
So Higgs in the sense of expectation value, not in the sense that it gives mass to something.
That's right. Yes, yeah, indeed. Yeah. And maybe I should put big quotes here. And there has been an industry about investigating whether the real Higgs can do this job, and that's another talk. But the short answer is probably not. Okay, so but I do not want to get into this. So we don't know. So let's just be agnostic about what this field phi is.
The Higgs had Goldstone modes which are eaten by the W's.
Yeah.
That is, the zeta is more like the longitudinal mode of the W in some sense. Whereas now the Higgs radial mode is the one that's being
that's right.
used as the Goldstone mode for inflation.
That's right. Yeah, indeed. Yeah. Okay. So let me define what the zeta variable finally is. So you take these slices. So let me draw them in 3D now. You take the slices, and in the Hamiltonian way of thinking about the general relativity, the ADM form, then the physical degrees of freedom are in the metric on the 3 slice. As I said, we've eaten this scalar perturbation, so really there are only fluctuations in the metric. So this is the metric on the 3 slice Hij, and it's going to have a form that looks like this. It's going to have some scale factor, a square root of t, that is determined by the scalar field, delta Ij, and then it's going to have a perturbation, and this is the definition, the standard definition of zeta. So for small zeta, it's just going to be, maybe I'll just write for linear theory, it's going to be 1 plus 2 zeta of x and t. And then you can have also gravitational perturbation. You can have some shear. And this gamma ij, as usual, is transverse traceless. It's a 3x3 matrix, so that gives you 2 degrees of freedom plus 1 of the scalar. Gamma ij, again, is a function of x and t. So these are the 3 degrees of freedom of the theory. And so you see from here that zeta is a modulation of the local scale factor. So it's some sort of breathing mode. So if I look at a point here, then non-zero zeta will just make the universe have bigger or smaller rulers, while a big gamma would just create some tidal force in a certain direction. And so this would be gamma, and this would be zeta compared to standard. Standard history would just have some scale factor like this. Okay, so this is my, I don't know if the picture is useful, but if you compute the local Ricci tensor, it goes like the Laplacian of zeta. Okay, so that's the Ricci scalar, sorry. Actually, it takes some work to quantize this in the ADM formalism, so I'll just tell you even though it's the quadratic Lagrangian, it's not exactly trivial. Well, it's a famous story, right? That there was some conference, I don't remember when, in the 80s, where people got the wrong answer 100 times, and then when they got it right, they realized that Mukhanov and Shibisov had already done it, right? So, but it's to get the correct gauge invariant variables and so on, it takes some inordinate amount of work. Now this is well understood. It's actually nicely reviewed in a paper of Maldacena, where he computed the non-Gaussianities from single field slow roll inflation. But so the background evolution is given by this. So you get the Friedmann equation. And, phi bar dot squared over 2 plus v of phi bar. And the Hubble rate changes very slowly as the field rolls down. Okay, so this is just telling intuitively what we expect. That the field's total energy sets the Hubble scale during inflation, and as the field rolls down, it depletes the effective Hubble rate. That's what these two equations are telling you. And then we call slow roll when we neglect the kinetic term compared to the potential. So slow roll technically means just take v of phi bar much bigger than phi bar dot squared over 2. Another way in dimensionless way of talking about it is to take the ratio of the Hubble, the change of the Hubble rates in Hubble units. And this is called the epsilon parameter. This is the definition. And we want to take it to be much less than 1. As long as this is true, the universe is accelerating, and end of inflation, we declare that inflation is over, that de Sitter is not a very good description when epsilon is 1. Okay? It will be useful also to assume that even this is changing very slowly. This is a little bit of a model assumption, which is related to the mass, the slope of this potential. This is called the eta parameter, and it's again the rate of change of the epsilon. So the second time derivative of h, if you wish, measured in Hubble units. I think I didn't mess this up. Yes, and we're also going to assume that this is much less than 1. And this sets two scales, which is unfortunate because you see that AS and S minus 1 and the tensor to scalar ratio are controlled by these numbers, but because you have two numbers, you have the freedom to hide the tensors. But if we use some naturalness arguments, then we'll see that we should probably expect tensors to be around. Let's get there.
Sometimes people use a conformal time, which involves A of t. Are these time derivatives?
These are with respect to, no, they're with respect to real time, yeah. Thanks for the, so I'm using this parameterization for the background metric. Yeah, so this is with respect to cosmic time, which is confusing because the best way to quantize is to go to conformal time. But anyway, for the definition, I'm using cosmic time. Okay, so after a lot of work, zeta and gamma will be at quadratic level. If you study the perturbations now on top of this background solution, will behave like massless scalars in de Sitter space. And then in the afternoon, you're going to get a little lesson about how to quantize in de Sitter space and whatnot. But you see, they're massless, they're dimensionless. And so what sets the size of the perturbation? So you have a typical energy scale, which is Hubble, so it needs to be measured in some units. And for the scalar sector, as I said, everything is controlled by the kinetic energy, right? If the scalar perturbation starts shaking at the same order that the scalar field is moving, then this becomes strongly coupled. So this would be essentially what I was calling F, but in slow row inflation, it's H over the square root of phi bar dot. Okay, and instead for gamma, well, it's coming from GR, so it has to be H over M Planck. Okay, so that's the expectation for the size. To actually get the scale dependence and so on, one needs to solve the wave equation in this background. And it's not terribly complicated, but I will just quote the final result. Because in the afternoon, we're going to get into some of the intricacies of doing this. So if you wish, the hard work is to prove that these are massless fields at the quadratic level, and to compute the coefficient in front of the action, because otherwise it's just two massless fields. And it's very important that they have different sizes, because otherwise you would predict that we have to see gravitational waves, which we haven't already. So this sets the hierarchy between scalar and gravitational perturbations. So the quadratic action for zeta, I'm going to write in terms of M Planck, but it's really fake. And you put an epsilon here. This is just to show that you need to break de Sitter symmetry. This needs to have an expectation value for this eating. For the gravity to have its meal, you need some non-trivial expectation value. So that's just to say that you can't send epsilon to 0. You have this scalar mode, so it doesn't really make sense in de Sitter space. So this is with respect to the background metric. This FRW quasi de Sitter metric. And then for the gravitons, then it's truly M Planck. It's even a factor of 8 if you do things carefully. And then each polarization mode of the graviton acts like a scalar field. Okay, so this is the action. So most of the hard work is to, actually it's kind of tricky to do this computation. Then you get this relative coefficient in the actions. Okay? So then let me predict the observables. So AS is going to be H over phi bar dot squared. AT is going to be H over M Planck squared. And S minus 1, this doesn't take a lot of work, but I'm just going to quote the result, is minus 2 epsilon minus eta. And we know this number. It's order 10 to the minus 2. And now, interestingly enough, if you look at the ratio of tensors to scalars, it's controlled by phi bar dots in Planck units, but therefore it's controlled by H dot over H, controlled by epsilon. Okay, so the tensor to scalar ratio is going to be 16 epsilon, actually. So the plausibility argument is we have measured this number, and these guys are probably same ballpark. Therefore, we probably should be around the corner at detecting something. Of course, you can just say, oh, epsilon is tiny compared to eta, but then you need to explain if you can generate a very big hierarchy between eta and epsilon hides this beyond detection. But it doesn't matter. We're going to try to measure this in the sky in the next decade. Okay. So the future. So right now we know that this is less than 10 to the minus 2, and in the future, near future, Lightsbird, for example, should a satellite experiment that is spearheaded by the Japanese Space Agency, but has contributions from many other countries, Italy, for example, INFN, so on. So R will be less than at least. We're either going to see something or R is going to be less than. We're going to improve by an order of magnitude in this measurement. Well, maybe obvious, but if we detect something, detection implies H is order 10 to the 13 GeV. Okay? So I don't need to explain to particle physicists that this is kind of cool, no? If the universe runs an experiment for you at 10 to the 13 GeV, then the obvious question is, can we do particle physics? So I have 10 minutes. Yeah. So in the last 10 minutes, I will. So it is plausible. Okay. So now this is the optimist take. Yes.
I want to ask a kind of stupid question, but R is basically AT over AS, right?
Yeah.
So it looks like H cancels out of that.
That's right.
You're just left with phi dot.
Yeah.
And then you go over there and you say phi dot is the square root of H dot.
That's right.
But then you said it gives you epsilon, which has a H squared in it too. Just wondered if I missed something there.
Did I mess up? Maybe I messed up the units.
So I think it's H squared over.
Yeah, maybe it's H.
Maybe one of these is squared.
Maybe it's H squared over, so that then you were. You're saying this, right? Yeah.
Okay.
Yeah. Sorry. Maybe.
Okay. Great. Thanks.
Okay. Yeah. Dimensional analysis. Yeah. I messed up. Sorry. Okay. So now, Arkadiy's question, what about higher point functions? So this has a not very glamorous name of primordial non-Gaussianity, which just means like probing statistics beyond the 2-point function. But maybe a better name for it is interactions. So now if I take this, so we just studied free field theory. We just studied, say, the 2-point function, the pair production of two scalar perturbations, or pair production of two gravitational waves. But what about if we take 3? What could go here in the middle? So there are many things that you could imagine happening. So let me open up the one thing is, by the way, time goes up here. I'm just looking at the correlation functions at the end of inflation. So if I repeat now, I hope it's not confusing. Time goes up, I'm just shifting the figure here, so time goes up like this. So what are possibilities? Possibility 1 is you compute some self-interaction, some correction to the linear sigma model, just some hard context term. This would be the FNL order 50 for which we have bounds right now. Here, just from locality, you see that this signal peaks around an equilateral triangle, right? Because each mode is stretched. The particles are produced, the triplet is produced at the same time, and they're stretched by the same amount. So the signal is the biggest when you correlate the same distances in the sky. So this, for this reason, this is called equilateral non-Gaussianity. It peaks around the equilateral triangle. The moment you try to make the triangle get squashed, you generate a hierarchy between the scales, and this, because of locality, you cannot do. But so that tells you that if you go to this squashed limit, so it peaks around the equilateral triangle. But if you take some squashed triangle, you generate some hierarchy between scales. So one of the guys has very long, this is in momentum space, okay? So one of the guys has very long wavelength. It was stretched for a long time during inflation. Well, these two other guys, 1, 2, 3, 2, 3 were stretched a little bit. So because we're not in the crackpot business, we need to fill in the picture somehow. There needs to be some mediator here. And then you can choose from a menu. Okay? The simplest thing you could do is you can just attach a 3-level particle here. And just this realization that you should think of this as some sort of scattering experiment where you use this non-Gaussianity as a particle detector created this logo people call cosmological collider physics. Okay? So, of course, you can imagine other things. You can put a loop diagram. You can put even like a 2-point function of a strongly coupled sector, this QCD-like sector. And I have to, in the afternoon, I'll tell you how to compute this simplest example. It's surprisingly complicated. In particle physics, first of all, this doesn't exist in flat space because there's some linear mixing vertex. You would be already raising your eyebrows. But the way to think about it is that it's more or less like a 4-point function, where this fourth guy is very soft and it sets the inflationary background. So if you think of this fourth guy as very long wavelength, it redshifts very, very slowly, and then it's sort of like a 2-to-2 type of scattering amplitude. And we know how to do this in flat space. It's 1 over s minus m squared. And I'll show you what 1 over s minus m squared is in cosmology. It's a complicated function with an interesting analytic structure and so on. But anyway.
Does the mass m have to be small compared to Hubble to get a...
So what sphere-X is looking for is this diagram in the massless limits. This, of course, is the infinite mass limits, and then there's everything in between. That just now people are using CMB data to put like stringent constraints on. So it was searched for just scalar messengers. It's called the quasi-single field inflation. But the most general thing, if you put a spinning particle here, for example, you modulate. So For example, if I put a spinning particle, you can think of these two guys as a polarimeter. So if I start moving this pair here along an angular direction, the signal will be modulated. And even this search has not been conducted with all detail in the CMB. So
just asking, in the case that the mass gets large compared to the inflation scale, then you reduce back to...
Then you reduce back to this. Yeah. Yeah, indeed, yeah. So this is, of course, most efficient and most spectacular of mass order Hubble. And I'll show you what happens in this case. But anything of mass order Hubble and below will lead to a non-trivial shape, which will interpolate between this thing and FNL that Sphere X is going to hunt for. Now I have 0 minutes, but I cannot resist but telling you about what I told you about what if I attach a graviton. It's just I think a cute thing. So what if I put a graviton here? What does the particle detector look like? Yeah, I'm running out of colors. Let me put. So now you would like this this to decay as low as possible, and here what saturates the decay rate is when you stick in a massless particle. So you would say, oh, I'm just going to stick in a massless spin 2 particle. It needs to be spin 2, otherwise there's no mixing. But massless spin 2 is the graviton itself, so we can't do that. What about a very tiny, very light, massive spin 2 particle? And then I claim it's forbidden by unitarity. So there's a cool thing about representation theory of the de Sitter group. So I'll just finish with that so you can think about it during lunch. So if you look at m squared over h squared, the allowed irreps of the de Sitter group, in then for scalar particle, for j equals 0, then you have 0, and then there's like 9/4, and there's even a sense in which scalar particles can be heavy and light, which is something that doesn't really exist in flat space. So the representation theory changes from this part. This is called the principal series, and this is called complementary series. So these are all allowed, and in some sense, all of these particles here behave like massless fields in flat space. They have power law decay, slow power law decay. So there are many ways in which a particle can be massless in de Sitter space, this whole range. And these are like standard massive particles of flat space in de Sitter space. So this is called the principal series. But now when you go to spin 2, there's something funny that happens. M squared over h squared. There's again 9/4. It's some accident that it's the same number where this principal series kicks in. And then the complementary series, of course there's the graviton here. Here's the graviton. But the complementary series stops. Okay? Stops at 2. So m squared equals 2. There's the complementary. And this is forbidden by unitarity. You see that one of the helicity modes of the spin 2 particle acquires negative norm. And that's so you cannot put a very light mediator here. So the fact that you can only go down here tells you that this will never decay as low as you could possibly. The analog of this FNL local that people look for with Sphere X, the claim is that it should not exist, so you should really see 0. If you see something non-zero, then you really need to do crazy stuff during inflation. That can.
I may not have understood your argument. You said in the case of j is equal to 0, anything less than 9/4 behaves like a massless particle in flat space.
Yeah.
For spin 2, you have this little region between 2 and 9/4. Does that not behave like a massless particle? The way it behaves like massless, it behaves like massless in the sense that the correlation function decays like a power law, but the power changes. So the lighter it is, the slower the decay. So here the slowest, which would be this FNL local. Now here you get
you get a little bit of decay, but if you would like to get the same decay as the graviton, you have a barrier. So that's to say, so here the decay rate would go like k long over k short, linear in k long over k short. While here, it can be k long over k short to an arbitrarily small power. So that's
Why can't it be the graviton?
Because it's the graviton here. You can't linearly mix with itself. So it would just be a self-interaction. It's derivatively coupled. Yeah. Yeah. That's right. So this is a funny, and last thing, and then we go for lunch. So this guy has 5 degrees of freedom as usual. This guy has 2. And this is a funny fellow. It has 4 degrees of freedom. So only the scalar mode decouples the longitudinal mode. And nobody knows if there's an interaction theory of this particle. It exists in representation theory, but people have not been able to build a unitary theory of this guy.
So no expectation for the size of the signal then if you look at that point?
There is some expectation. You would decay like so if I call it K1 and K2 or the K3, then you would expect that the signal decays as power 1. And so the FNL order 50 that we equilateral goes like K1 over K2 squared, and FNL local goes like K1 over K2 to the 0. So it's in between. So you would be able to do better than equilateral, but not as good as local. Yeah, by the way, this is called local. The most non-local thing you could imagine doing, sticking in a massless particle, but again, bizarre historical reasons, it's called the local shape of non-Gaussianity. I can tell you offline why. Okay, let's go for lunch.
Thank you.